exam 2, so just modify that note in the schedule. Exam 2 will cover through lectures 9 through 20, so that'll be through shear center, and then we'll just bump circular beam to exam 3. Mainly because, a little slow to finish up that lecture. It's also kind of a lot to digest in one lecture, so I think it makes more sense to just kind of give you more time to wrap your heads around that topic before the second exam, and then we'll just tie it into homework 7 instead of homework 6. So, sound good? Okay. All right. So that exam is, a week from Wednesday. All right. So next week, exam 2. Similar to exam 1, it'll be 2 problems that you solve equal amount of points. Topics start with finite element analysis, and then it'll go through the shear center. So you can bring a note sheet as before, and same deal. Okay. All right. So we'll continue with circular beams then. Just wrap up this lecture. So we talked about how your strain is not linear with y along the depth of the cross-section in this case. And really this is because, when we calculate strain and we define it as the change in length divided by the original length, that original length will vary with y, right? If your beam is pre-bent, then the original length at the outer edge is going to be longer than the original length at the inner edge, right? So because that denominator is also varying with y, that's why we end up with this nonlinear strain distribution. All right, so skipping ahead then, we're halfway through page 3. So we got to the point of defining this location of the neutral axis. And this term in the denominator, this is what you'll see in these tables, or this handout, right? So for different shapes, you have the formula to solve for that denominator term based on, and it's all based on these distances from the center of curvature, before loading. So that's what this line represents. From that point to the near side of the section, and then from that point to the far side of the section, that's your B and A. And then any cross-sectional dimension values that are relevant to that shape. All right, questions so far? Great. So now we need to, our goal is to determine an equation that will relate stress to the applied loading, right? So we're gonna now bring our moment into the picture. All right, so we have M is equal to the integral over the area of y times normal stress, where y represents the moment arm, and the integral of the stress distribution represents the net force. So that's going to be Young's modulus then, if we make our substitutions, for stress. Young's modulus can come out front, and then we have d theta over d phi times the integral over the area. And then in brackets, we'll have lowercase rn over lowercase r minus 1. And then in a second set of brackets, lowercase rn minus lowercase r. And that second term in brackets is the variable distance y. All right, but we previously noted that the integral over the area of that first term, rn over r minus 1, is equal to 0. So this means we can write m is equal to negative capital E d theta over d phi times the integral over the area of lowercase rn minus r, or evaluating that integral gives us capital E d theta over d phi times, in brackets, capital R, capital A, minus lowercase rn times the cross-sectional area, capital A. All right, and then we also had defined lowercase e as capital R minus lowercase rn. All right, remember, capital R is the radius to the centroid, and lowercase rn is the radius to the neutral axis before loading. So now we can say m is equal to capital E d theta over d phi times lowercase e and capital A. Or we can solve for d theta d phi as m over capital A lowercase e capital E. And then we can write our expression for normal stress. Sigma x is, in parentheses, lowercase rn over r minus 1 times m over a lowercase e, or simply m times y over capital A lowercase e and lowercase r. So this would be the formula for normal stress in the case of pure bending. All right, so the only load applied is a moment. If we were to introduce an axial force that was acting on a circular beam, then we'd have something that looks like what's sketched on the next page, right? So an axial force, we'll sketch, if we kind of take a cut through here, right? We'd have, and look at the top half, we'd have that force F. Then if we make a cut through the beam, that would generate an axial force. We'd also have a moment due to that applied force F. That moment would be F times capital R. And the normal force at that cut would be equal to F in this location, right? Of course, if we made a cut here, then we'd have the normal force being some fraction of F, right, based on the angle there. And you'd also have a shear force, right, if you were to cut somewhere not right at the horizontal side. So you'd also have a shear force in that case. But for circular beams, shear is really minor, so we can generally neglect or simplify our shear stress calculations. So I'll make a note of that in a moment, but basically this normal force and will generate a uniform stress distribution over the cross section with the resultant at the centroid. So we can use the equation for normal stress from before for moment, right? My over a lowercase e and lowercase r. So make sure that's consistent. Yeah, that's what I wrote before. And then add a term for the normal stress. So that would just be n over a. So that would be the normal stress due to the presence of a normal force. And then I'll make a note down here, right, that shear stress is typically very small. And can be approximated using straight beam equations. All right, so when we get into the next lecture, which is going to be focused on strain energy, we'll get to a page where we apply that to circular beams. Probably not today, that'll probably be on Wednesday. And when we do that, I'm going to say, actually, in this case, shear stress for circular beams, it's okay to even simplify it further and just use the average shear stress formula. So you don't have to go through the more complicated shear stress calculation that involves the first moment of area, Q, right? We can keep it simple since tau is not going to be a big player for circular beams. All right, so then the last half of this page is just some additional commentary. This is more bonus information, so I'll just note here this is FYI, bonus info, don't need to know it for this class. But it talks about how there is also going to be some radial stress associated with these beams. So you can see the formula for calculating that radial stress. And these values are just estimates, really, right? So it's not exact, and especially, right, if the loading includes axial and transverse shear force. So we're not going to be calculating that in this class. We'll just be thinking about the longitudinal stress for circular beams due to moment and or axial loading, right? And then maybe a simplified estimate for shear stress. So, all right, so any questions on circular beams? We will come back to circular beams, but this is probably the most challenging subject on circular beams, this lecture, just introducing the stress equations. What we're really going to be spending more time on with circular beams is going to be related to finding deflections and reactions using Castigliano's modified theorem for finding deflections. All right, so before we get to Castigliano's modified theorem, we need to talk a bit about strain energy. And we talked about this a little bit before when we were deriving, I forget what context it was. Was it the beam bending or finite element analysis?
Plate.
Huh?
I think you had to do the plate.
Plate? Yeah, it was early on in the semester, and it was, well, it's not too important to find it, but
Plane strain. Plane strain.
plane strain. Okay, yeah. So we introduced it after plane strain. Okay. Yeah, and then I think we used it for something, but not a lot, right? Before, let's see.
Yeah, we had it for plane strain.
Okay.
We used it in homework.
Do you use it in a homework? Okay. Yeah, this is what I'm thinking of. Right, so Hooke's law. Yeah, so we introduced it in the context of Hooke's law. So we're going to come back to this concept and take it a lot farther. All right, so as you recall, strain energy density is defined as the area under the stress strain curve. All right, so, and we use the lowercase u to represent that value. Now this is showing the stress strain curve for a uniaxial load. Right? If we integrate that strain energy density over the entire volume of an object, then we get the total strain energy, which is capital U, and that's going to be equal to 1/2 times the integral over the volume of the normal stress times the normal strain. Now that's just for the uniaxial case, right, where you only have normal stress in X. We have the potential for 3 normal stresses and 3 shear stresses to be acting all at the same time, right? So we have to develop a generic expression for strain energy that incorporates all 6 stresses. But then we'll simplify it back down and just deal with plain conditions for a while. So if we have all 6 strains, then this expression really expands. So we'll just write the generic integral of strain energy over the volume, or strain energy density. So that would be 1/2 times the integral over the volume, and then in brackets, normal stress in X times normal strain in X, plus normal stress in Y times normal strain in Y, etc. Right? You can pick up on the trend and see where I'm going with this. And then we have all the shear strain terms and stress terms as well for every plane. So we're going to consider beam bending, all right? First, anyway, we'll consider a few other types of loading as well. But first, we'll just consider beam bending. In that case, this will whittle down, right, to a much simplified version. So for beam bending, we only really have 2 stresses and 2 strains for the loading conditions shown where we have transverse loading in the XY plane. All right, so we'll note only 2 stresses and 2 strains relevant. All right, so Specifically, normal stress in Z direction will be 0, and the shear stresses in the XZ and YZ planes will both be 0. And also, for beam bending, the normal stress in Y will be 0 as well. So we're neglecting consideration of the bearing stress on that material where the load is applied, and just considering the stresses due to the bending of the material. So our strain energy equation will be 1/2 times the integral over the volume of sigma x times normal strain in x plus tau xy gamma xy. And that represents the total energy, or I should say the total strain energy. And if we make our substitutions using the constitutive relationships for stress and strain, we can rewrite this as 1/2 times the integral over the volume of, in parentheses, sigma x squared over capital E plus tau xy squared over capital G. Or capital G represents that shear modulus that we talked about before but haven't talked about in a while. So all right, so as you can see, strain energy is a function of the normal stress and the shear stress in the XY plane. We can also then say that it's a function of capital F, capital M, and capital V, right? The internal forces that the beam will experience due to the transverse loads. So we'll keep the potential for an axial force in there for now, even though we're just thinking about beam bending. I'm going to say U is a function right, since we can write normal stress as a function of moment and axial force, where normal stress is negative my over I plus capital F over A, and shear stress is VQ over IT, or sometimes taking the average shear, which is just V over A. Sometimes that's appropriate, as in the case of circular beams. All right, so now we're going to separate our concept of shear energy into shear energy. We're going to separate our concept of strain energy into the component that is contributed by shear behavior or shear deformations, and the component that's contributed by axial deformations, which would come from moment and axial force. So first, we'll consider the shear contribution to strain energy. And I'm going to call this capital U with an S subscript. All right, so for every finite length along the beam dx, we'll define the change in the shear strain energy as 1/2 times the integral of tau xy squared over capital G over the area, all right? So since we're just considering a finite length, that takes care of one dimension, and so we just need to integrate over the cross-sectional area. So bringing out constant values in front of the integral after making some substitutions for shear stress, we have capital V squared, representing the internal shear force, over 2 capital G and then capital IZ squared times the integral over the area of capital Q squared over lowercase b squared. And we have to keep Q and B inside the integral because technically those two terms could vary along the depth of the cross-section, right? And so we're going to simplify that term to a letter K, which we'll define in a moment, but it's essentially a shear shape factor, times V squared over 2GA. All right, so K represents the shear shape factor. And the definition of that is A divided by L squared times the integral over the area of Q squared over B squared. All right, and this, as above, this is the generic expression where Q and B can both vary along the depth of the cross-section. If we simplify it to a section that has a constant width, then we can say that's equal to A over L squared times the integral along the length y, Q squared over B dy. So that would be for a constant width B. Now that shear shape factor depends on the cross-section geometry. There on the next page, there's a summary for different kinds of common shapes and what the shear shape factor is. We're going to spend the rest of this page deriving the shear shape factor for a rectangular cross-section. So on the next page, you can see that it's 1.2. I'm gonna show you how to get that value. But then after that, you can just use that table to look it up. So. All right, so if we have a rectangular cross-section to consider, all right, these values are noted here. You got the variable distance y measured from the neutral axis, and we will define the shear stress equation that we are familiar with, VQ over B and I, about the z-axis. So that would be equal to V times lowercase b, representing the width, which is constant for this section. And then for the rest of the area, the other dimension would be h over 2 minus y. All right, so that would be the area of this shaded section, which, remember, that Q term is the area of the section from the point where you're calculating the shear stress to the nearest free surface. And then the rest of that hue term is the distance from the neutral axis to the centroid of that section. So that would be the y1 bar, which in this case, I'll note y1 bar is equal to h over 2 minus 1/2 of h over 2 minus y, right? And that's that distance there. So that simplifies to 1/2 of h over 2 plus y. All right, so in the numerator, we have this representing y1 bar, and this representing a1. And then the denominator, we have b and iz. Since b cancels and iz is bh cubed over 12, we can simplify that shear stress expression, and I'm going to bring in that xy just as a reminder that this is shear stress in the xy plane. That'll be 6v times, in parentheses, h squared over 4 minus y squared. And then in the denominator, cross-sectional area times h squared. All right, so that's making some substitutions, noting that A is equal to B times H. So then our shear strain energy is 1/2 times the integral over the volume. All right, so now we're accounting for the whole volume, not just a finite length dx, of tau xy squared over capital G. All right, so that's dA dx to get volume. And so bringing the G out front and some of the another constant, so we can write that as 1 over 2G times the integral of, in parentheses, 6V over AH squared, and that quantity is squared, times another quantity, which is H squared over 4 minus Y squared, and that quantity is also squared, times B dy dx. So B dy, if B is a constant, represents dA. So then for every dx, oops, there we go. We have our shear strain energy is 1 over 2G times 36V squared over A squared, H to the 4th, times B. All that is constant with respect to our dy, all right? So we can bring that out front of the integral, and then we will integrate along with respect to y. So we'll integrate along the depth of the cross-section, and I'm going to take that from negative h over 2 to h over 2, since we place the origin at the neutral axis, or at the centroid there. And that's going to be integrating h to the 4th over 16 minus 2y squared h squared over 4 plus y to the 4th. Evaluating that integral, and I will spare you the details unless you really want to see them, we get 1.2 times the integral of capital V squared over 2GA dx. Or I guess this is now going back to right, back to the general equation that has dx in there, right? So we've got the v over 2GA inside the integral now. All right, so that leads us to finding out that our K, our shear shape factor, is equal to 1.2 for a rectangular cross-section. Questions? The axial contribution is a lot simpler. So
V squared over 2GA just integrates to 1, basically?
no, so that is, that comes out here, right? So what did I say? Oh, for every dx, we have this,
Okay.
right, where K is the 1.2. Yeah, and so then taking this and integrating it along dx, we get this. Yeah.
Gotcha.
Yeah. All right, so next page has those shear shape factors. Now we'll do the axial contribution to strain energy, and that axial behavior, that axial deformation is what we're really looking at, right? Because strain energy comes from deformation. So that's going to be caused by beam bending and maybe normal force if you have a normal applied force. All right, so once again, we'll just start by considering a finite length dx. So for each dx, the change in axial strain energy, all right, so we'll call that UA, is equal to 1/2 times the integral over the area of the normal stress squared over capital E dA. And we, of course, know normal stress is negative m times y over I plus F over A. And so from a normal force, let's see, or axial force, normal stress is F over A. So the sigma squared over E term integrated over the area can be written as integral over the depth y of F squared over capital E capital A squared times the width B dy, or capital F squared over capital E capital A. So that, of course, is for a uniform width. And that would represent the axial force component of the axial strain energy. the bending component, we're going to use sigma is equal to my over I. And the understanding that y squared integrated over the area is the moment of inertia. So the integral of sigma squared over capital E for bending is going to be m squared y squared over EI squared integrated over the area, which is m squared over EI squared, right? Because we can bring all those outside of the integral, and then we're just integrating y squared over the area. Since that is your moment of inertia, we get m squared over EI. And this represents your bending component. Of the axial strain energy. So the total axial strain energy is represented by the integral of m squared over 2EI plus f squared over 2EA with respect to x, right? So integrated along the length.
Where's the 2 in the denominators coming from?
So, yes, good question. Here. Yeah, so I kind of dropped this when I was doing these guys, right? But for each dx, there's this whole integral is divided by 2. Yeah. So yeah, so I guess to clarify that or avoid confusion, I should really modify my notes down here to say, right, then take that and divide it by 2 to get your components of the strain energy. And that's coming from here. All right, so now that we have defined the shear contributions and the axial contributions to strain energy, we have what we need to write our expression for total strain energy. So that's just capital U is equal to, and this is again integrating along the length. So integral from 0 to L of m squared over 2EI plus f squared over 2EA plus the shear shape factor K times V squared over 2GA dx. And then if you had torsion at play as well, you could simply just add a term for torsion. And that would be similar to the other expressions. It would be t squared over 2gj. So do a really quick example, and then Yeah, we'll have to finish this lecture up on Wednesday for sure. So, a quick example, very simple one, just an axial only situation, all right? We've got this column that is fixed at one end and has an axial load at the free end. So we want to find the strain energy in the column. So if we make a cut, we do that to find the internal forces that we need. All right, so we have our applied load P. The internal axial force will be equal to P. We have no shear, no moment, right? Because we only have the axial force at play. So M equals 0 and V equals 0. So our strain energy is just going to be the integral from 0 to L of P squared over 2EA, which is P squared L over 2AE. And I think it's usually a good idea to do a little gut check with units. So in the numerator, we have force, we'll say pounds for force times length. We'll use feet for length. And then in the denominator, we have length squared and E, which is going to be force per length squared. So that lands us on pound-feet, which is an appropriate unit for energy. Right. Questions? Okay. Good deal. Well, that is a good stopping point. Next time we'll apply it to a beam example, and then we'll look at what happens if we have a circular beam to consider. Then we'll get into Castigliano's modified theorem.